Welcome back. In this video, we're going to talk about two-dimensional graphics and how to dress up your two-dimensional plots. So for two-dimensional graphics, there's two main commands that we will be using, Pcolor and imagesc. And for reasons you'll see, I like to use imagesc a whole lot more. Let's just get right into this. Let's start with a new script. And I like to always work from a script instead of the command prompt so that you can always see what has been typed. So first line, we'll give it the name. Let's call this Demo Graphics 2D. And so I will copy. We will save that, and we're ready to go. Next thing I'll do is I'll hit return a whole bunch of times and go back up, and we're ready to start. First thing in the code, always initialize MATLAB. We will close all open figure windows. We will clear any text that may be in the command window, and the absolute most important is to clear memory. Okay, so let's just go ahead and create an array of numbers. So let's say A is rand 3 by 3, and I'm not going to put a semicolon there, so when I run my program, I can see my numbers. Now, one thing that's going to happen every time we run it, those numbers will change. That can make it hard to troubleshoot. So here's a little trick so that we get random numbers, but they're the same random numbers each time. We'll give the randomizer a seed, and if it has the same seed, we run it. Okay, we see all random numbers, but now every time we run it, we see those same random numbers. And this really helps for troubleshooting because if you catch a problem, you can rerun your code to zoom in on it, whereas if those random number changes, sometimes those problems can disappear. So that's a neat little trick to use. Let's go ahead and plot this. And there's, first of all, the image command, image sc, and the sc means scale. So it automatically will scale your numbers so that the colors that appear span the full range of the data that's in A. So let's go ahead and imagesc. And right away, we can notice some things. We have an array that's 3 by 3 numbers, so it should be the same width as the height. And right away, we're looking at a rectangle, and that does not seem right. And for two-dimensional graphics, I almost always will follow my calls with an axis equal. That makes the X and Y axes the same proportion. So squares look like squares, rectangles look like rectangles that are in the correct proportion. So I always do that. But when we just say axis equals, something mysterious and frustrating happens. We have this ugly white space that we probably don't want there. We're not controlling it. It's wasted space, and I think very unprofessional. So almost always I will follow the axis equal with tight. And tight brings the edges of the axes right up to the data. And I think that looks a whole lot more professional. And right away, we see 3 by 3 colors. And those colors clearly will represent the numbers in our array in some way. But we don't know how those colors map. And so we might want to add a color bar to that. We'll hit run. And now we can see what color corresponds to what value. If we slide our figure window over, we can take a look at this. So in this upper left quadrant, it's kind of a bright blue. Yeah, maybe around this color, so it's a 2.3-ish. And if we look over here, oh, 2.2. So that's what that number represented. Here's sort of a greenish, yeah, 0.65-ish. And we see, oh, it's a 0.67. So from the colors and this color bar, we're able to obtain the values. And if you watch the one-dimensional graphics, I'm also looking at things like font sizes and all that, and we will eventually get to all that. All right, so we have a 3 by 3 array of numbers. imagesc has shown us 3 by 3. Let's go ahead and look at what Pcolor will do. Suddenly, our 3 by 3 set of numbers has, at least in terms of the graphics, become 2 by 2. And it's not exactly 2 by 2. What it's doing is it's placing the values now at the edges of these sections or pixels, if you will. So For me, for my day-to-day work where I am plotting digital data and I want to go in and explore what the actual value inside these pixels are, I can't do that with Pcolor. And so what this is doing is it's picking some color that's sort of an average of the values that are either of the edge. So Pcolor does a very good way of smoothing and interpolating the data. So if I'm plotting smooth functions and I'm generating that very last figure that's going to go in a publication, I'll use Pcolor. For everything else, I'm using imagesc. So a 3x3 array of colors, I know I have a 3x3 array of pixels, and I can zoom into any one and figure out exactly what that value is at that array position. The next thing I'll point out here is notice the horizontal axis. So 1, 1.2, 1.4, we're increasing going up. Let's go back to imagesc and run it. And now notice the numbers are increasing going down. And that bothers a lot of people. The reason it's going down is imagesc is drawing what MATLAB thinks is a matrix. And this is actually how the subscripts on matrix element like A under subscript 1, 2, this is what the subscript means. The first subscript is the row number, row 1, row 2, row 3, and that does increase going downward. And so like A sub 1, 2, that second number is the column. So 1, 2 would be this number. This is A sub 1, 2 right here. So MATLAB thinks it is drawing a matrix. That's why the numbers are increasing going downward. If we're not drawing a matrix, we're drawing a function, well, then our vertical axis is upside down. And that bothers some people, but that's easily fixable. We can go in here and say set, get current axes, YDIR for Y direction, and just set it to normal. Right now it's set to reverse by default in imagesc, and if we run it, now our numbers are increasing on the vertical axis, and we notice all the numbers have also been flipped vertically because the 1, 1 element is still always corresponding to this particular value. So that's how to fix that. I don't ever do this step because I'm used to just now looking at the numbers increasing going downward, and it doesn't bother me. So you'll rarely see that in my code unless I'm trying to make imagesc look like Pcolor. Let's go ahead and do something else. Let's increase the number of points here. Let's go up to, let's say 200 by 200. Now, this will just look like crazy noise, and I don't want to display it to the command prompt now because we have very large data. Okay, so not surprising. Let's type in Pcolor and see what happens. Notice how dark this is. And in fact, if I were to up the number of points here, my plot is going to go completely black. Now, why is that? We can discover why that is if we plot less points. Look at what Pcolor is doing. It's putting black lines between each of those pixels. And so when we have a lot of those pixels, all we're seeing is the black lines. Well, what if I still want to plot this many? What I would do is I would follow my Pcolor with a command like shading interp. And now if this were smooth data, and later in this video we will have smooth data, we would see nice smooth data here, but we're not seeing those black lines anymore. So that's how that is fixed. So as I mentioned, in my day-to-day activities, I'm using imagesc almost all the time. I only ever jump to Pcolor if I have a smooth function and I'm generating that final plot that's going to go into a presentation or publication or something like that. So we will use imagesc here. Okay, so let's erase all this and start over. The first thing I'll do is I'll define function size. And first I'll define its physical size. So the x-axis will have a size of 2. So we'll have the x-axis go from 0 to 2. And for right now, we'll just make the y-axis the same physical size, 2. And 2 what? Well, it could be 2 inches, 2 feet. We're not throwing units into this, but it's 2 of whatever units we're interested in. We also need the number of points, and 128, nice binary digit, ny. Now, I like to have my pixels as square as possible. So if I chose, let's say, only 10 points, even though it's the same physical height, if I'm using fewer points, my pixels will look like toothpicks. They're going to be very tall up and down, but skinny left and right. And so to proportion this, here's how I like to do it. I will say round, and I'll type nx times sy over sx. And what this will do is it will pick the number of pixels in the vertical direction to try to make those pixels as square as possible. So we can go ahead and run this, and we'll type in nx, and then y. What we see is the same number because they're the same physical height. Now, if I, let's say, went up to 3 for the physical height, so my grid will be taller than it is wide, what we see is we actually have more points, and we have enough more points that those pixels are as square as possible. Now, I'll go back to just being 2 by 2. So that's my function size. Now I'll show you something really neat that I use all the time. I use this when I'm doing image processing. I use this when I'm processing electric fields, and I just need some kind of randomish function to test my algorithm on. This works really well. So we'll go ahead and generate random function. The first thing I'll do is I'll define a parameter that essentially controls the randomness. The lower the number, the slower the randomness will look. The bigger that number, the faster the randomness will happen. Okay, now I need to calculate a bunch of start, stop, index arrays, because what I'm going to do is I'm going to generate a bunch of random numbers. I'm going to FFT it. I'm going to zero out a bunch of that FFT, then inverse FFT, and it's essentially a digital filter it's a low-pass filter, and we'll get smoothed out data. So I need to calculate start, stop indices in the FFT of where to zero out. And here's how I like to do that. So the start index along the horizontal axis will be 1 plus floor. And let me explain what I'm doing here. Array indices in MATLAB start at 1, and that's because in MATLAB it's not really an array, it's a matrix. And matrix indexing starts at 1. So if I were just to say floor and have something in here, I could potentially get a 0, and I don't want that. So I want to start at 1. Now inside here, I want to do my randomness parameter times nx. And what I'm trying to do is I'm trying to get a number here that's an integer. And it's going to go 1, 2, 3, 4, all the way up to possibly nx. But now here's a problem. If f happens to come in as a 1 times nx, rounded down, it's just nx, then I add 1 to it. Now it's too big. It does not work. And so what I'll include in here is a 0.999. Then you can put another 9 if you want to. That will prevent this from being nx. It'll just be slightly shy of nx, depending on the value of f. And so we're sure to get a number from 1 to nx, nothing less, nothing more by doing that. All right, nx2 will be nx minus nx1 plus 1. That just gives it symmetry for the stop index. So if we start 10 elements in, we will end 10 elements from the end. Let's going to run that, just make sure I don't get any errors. I will copy and paste this and do the same thing for the y direction. I'm going to run that, just make sure I get no errors. Okay. And we can go quick look at the numbers, nx1, nx2, ny1, ny2, and that looks good. All right, now we'll go ahead and actually calculate the function f equals rand nx by ny, and I'm going to subtract 0.5 because rand creates random numbers from 0 to 1, and so there's a DC offset, so we'll get this spike in the middle of our FFT if we do that. So I like to subtract 0.5 or subtract the mean or something like that. It gets rid of that DC component, so our FFT looks better. Then we'll finally FFT that. We have to say FFT2 because we're doing a 2-dimensional FFT. It will still look like a bunch of random numbers, but it's got the right phase built in so that if we inverse FFT it, we'll get a purely real function. Now we'll go ahead and we'll zero some things. We want to zero from nx1 to nx2 all the way up and down. Set that to 0. Then we're going to do the same thing, but all the way left to right, from ny1 to ny2 equals 0. Don't worry too much if you're not following everything I have here. You can always copy and paste the code, and you'll have this neat little random generator. Okay, now it's been zeroed out, so all we have to do is inverse FFT, inverse FFT2, our f. Now, just because of, maybe we don't have an odd number here or other little numerical artifacts, we could end up with a small imaginary part. So we'll just throw that out by putting in real here. All right, and align the equals because I'm strange that way. And that should work. Let's go ahead and just look at it real quick. imagesc f. All right, we have this nice random function. Let's go ahead and increase this number and see what happens. And notice that increases the frequency of the noise, if you will. And at some point, we can come too low and it doesn't really work. We just see kind of a sine function. That didn't work too bad. Let's try a 0.02. Anyway, you get the idea. Let's stick with 0.02. And so there's our function, 128 by 128 points. And now we're back to trying to make this look good. And so I'm looking again, this looks like a rectangle. The font sizes are too small. Nothing's labeled. And let's go ahead and do all of that. Well, the first thing we want to do is think about the axes. So we're going to have to generate arrays which tell us the position of each pixel along these axes. So that's what we'll do next. So we'll call it function axes. So dx is the width of the pixel. So if we have a physical width of 2 and we have 100 points, so then 2 divided by 100.02, that will be the physical width of a pixel. So it's the physical width of the grid divided by the number of points. Now we can create our x-axis. Well, the center position of each pixel will be 0.5 all the way up to big NX minus 0.5 times dx. This is now an array that will go from half of dx all the way up to nx times dx minus a half of a dx. So basically it's going from 0 to 2, but it's the center position of each pixel, so it'll start a little more than 0 and end a little bit less than 2. Let's go ahead and run that. And that's simply because it's the center positions of each pixel. So right, a little bit less than 2, and it starts a little bit greater than 0. Now we'll do the same thing for the y-axis. Now, even though I've chosen the numbers to be the same, and you might think, well, why am I repeating these calculations that are just going to end up being the same anyway down here? And that is kind of a waste. However, by repeating all these calculations, if I were to change this to a 3, everything else will work. If I just kept copying the previous calculation, if I change that to 3, I'd have to go fix a whole bunch of other stuff. And I don't like writing my codes that way. Okay, so now we have our axes. Now when we say imagesc, we can go in and type in XA, YA, F. Now there's one other problem. And where can we see it the clearest? Okay, let's start here, rand. Notice we told it how many points wide by how many points tall. Well, remember MATLAB thinks it's handling matrices. And in fact, this first number is how tall the array is. And the second number is how wide. Let's go ahead and watch this. Rand 3, 2. Notice it's 3 tall and 2 wide, and that's backwards. We like to think of that first number being the horizontal position and the second one being the vertical position. So the way we think is backwards the way MATLAB is doing that. And so my way through that is to do everything as if it's X first and then Y, so everything's intuitive from everything you've learned. The only difference is when you go to plot it, what we have to do is remember to transpose it with a dot apostrophe. So by the way, just the apostrophe does a transpose, but it also calculates a complex conjugate of every number in there, something called the Hermitian transpose. If it's all real numbers, that doesn't make a difference. But if you have complex numbers, it will conjugate everything. So a dot apostrophe is just the ordinary transpose and won't conjugate anything. We're dealing with all real numbers, so that's not really needed. So anyway, here we are. Now we have our axes, 0 to 2. And 0 to 2 going from top to bottom. We know how to fix that if that bothers us. I'm used to that. It doesn't bother me. So we're not going to fix that. Yeah, maybe we will. You know what? Let's go ahead and do it. Set GCA wider normal. Okay. So now our numbers are increasing going vertically, something I never do. And that's why I sort of battle with myself doing that here. Okay, so we're going to draw the function. And we do an imagesc. Maybe also, since this is smooth data, maybe we wanted to do a Pcolor. And in which case, the default will be normal, so we don't even need that command. Go ahead and do it. And oh yeah, we forgot about all these little black lines and stuff, so we'll follow that with a shading interp. Okay, and all that looks good. Notice our numbers are changing every time, and that kind of bothers me. So what I will do is, let's just do a rand seeds here. It gives the appearance that something's changing from iteration to iteration. Now we're going to get the same random number each time. So we'll go with that. Okay, shading interp. Let's go ahead and now set view. And this is where we're going to fix a lot of different things. So we're going to do an axis equal because we know that that should be square, but it's a rectangle. So we run it. Okay, now we get the square, but we have these ugly white spaces. We fix that with an equal tight. And so almost always in 2D graphics, always you'll see in my code axis equal tight. All right, the fonts look a little bit small, so get current axes, font size, and let's pick, I don't know, how about 18? And let's also put a big fat line around the outside. Line width 4. Thicker than that, it starts looking awkward. And that looks pretty cool. See the black line going around the outside. All right, what's next? Let's label the axes, and let's also fix our tick marks and how these are labeled. Notice we have a significant digits problem here. So we have a 1, and then the significant digits jumps to the left, and it just takes somebody's eyes an extra fraction of a second to interpret that. So if you're giving a presentation, this will draw attention, and so we want that to be a 1.0. The only exception to that really is when we have a 0. We'll just give that a single digit of a 0. So we want to fix all of these things. Let's go ahead and do the x-axis first. Let's set the x-axis limits, and that's essentially going from 0 to sx. So we'll do that. Let's run it, make sure no errors happen. Okay. Now we'll go in and we'll set up our tick marks, and these we're going to go from 0 in steps of 0.5 all the way up to sx. And our labels, we will just have an empty sequence, and we'll go calculate all of them. For m equals 1 to length of t. And so what we're doing here is we're creating an array of our tick marks along the horizontal axis, and this is a sequence. And it will be a sequence of strings where each string will be our label for the tick mark. That's how MATLAB does things. So we start off with an empty sequence. Sequence has the curly braces. All right, so the mth string in this, we will use num to string. So num to str to do this. We give it the number, it's the mth value in t, and then we'll give it our ANSI formatting. So this will be number, point number. So 1 decimal, 2 digits total, or 3 characters wide. All right, then we'll say set, get current axes, x tick, and we'll give it the tick marks, x tick label, and we'll give it L. Now let's run it to make sure we haven't made any mistakes. Okay, looks pretty good. Well, one thing we made a mistake. We should not have 0.0 for something that's exactly 0. This is one exception. We just want that to be perfectly 0. So we got to go ahead and add that special case. If t is 0, then the mth string in L will just be a perfect 0. Otherwise, do it the way we were doing it, with num to string. Let's go ahead and run that. And now that looks pretty good. And we'll label it. Let's label it x-axis because I guess I'm not having much of an imagination to do anything else with it. X-axis. And, we might even want to give it a different font size. Let's give it, I don't know, font size. Usually a little bit bigger than the numbers looks pretty good. Let's see what that looks like. Okay, so there's our label. Now there's a problem here. This X is actually a variable, and formatting guidelines tell us that should be an italicized Roman font. And so a neat way that we can do that is use a LaTeX interpreter. So let's actually change the interpreter to LaTeX, and we'll go ahead and run that. Well, it changed the font. Now we have a Roman font, but notice that is not italicized. And that's because just doing it this way, it's going to think that this is standard text. If we want something to be math symbols, we'll encase that in dollar signs. Now we have x-axis. That looks pretty good. Some people might want to hyphenate that. That's fine. I just chose to have a space there. But I think that looks pretty good. We'll copy and paste this and do everything again for the y-axis. And we'll copy everything again, even though it's doing almost the same thing, like when we calculate these ticks and labels, we might change something up top and the rest of our code will still work. All right, y-lim 0 to sy. Our tick marks will go from 0 to sy. Set GCA, now it's going to be y-tick and y-tick label. It will be a y label instead of an x label. It's y-axis, and that should all work. Okay, and we'll probably give this a title to let us know what we're doing, and I'll give the title up here under Set View. And let's call this weird function f of x comma y. And I usually like titles to be a little bit bigger. Let's stick with what we did down below. And we'll run that. Okay, now again, this f of xy, that is a math thing. And that should be properly formatted. So we'll go back to the LaTeX interpreter. So let's just go to the next line. So we use 3 dots, we can come to the next line, and we'll say interpreter LaTeX. And now if we run it, it changes the font to Roman, but notice it has not yet formatted that correctly. That's because we have to put the f of xy inside dollar signs to say that that's actually math symbols. And I think that looks pretty good. So in this lecture, you saw the key difference between Pcolor and imagesc. You saw what it did with the y-axis, how it handles the numbers. We saw how to dress up the axes, label the axes, and even label the axes with LaTeX. And we could easily put equations in here. Let's just go ahead and do that for fun. I know this is not x squared or anything like that, but x squared. So we can have all kinds of equations, square roots, any kind of symbol that LaTeX would have. So I hope this is helpful to you, and I hope you can generate very good graphics using what was taught here.